Okay, good morning. Let's get started. I just realized the class is almost over because, I guess next week is the last day of class, right? So, and there's a presenter talk. There's a colloquium tomorrow. If you get a chance, try to drop by. He's pretty well known. He's done a whole bunch of stuff all over the place. I think he has like 750 publications, which is kind of humongous. So one of the things that I would have loved to do in this class is kind of introduce concepts beyond the basics, just to see what people are working on in research or what have you. But unfortunately, there's not too much time, right? So what I want to do for the next few lectures is try and tie it together, because one of the things that people get away from operating systems classes is they assume it's a whole bunch of the LRU, FIFO, and all those like policies, right? But not the big how it will affect you regardless of whatever you do in life, right? Because it's kind of in the middle, right? So I want you to away. So hopefully we'll go through some of the stuff here. We'll try to design an operating system in class for different kinds of devices like PDAs, laptops, and stuff on Friday, and then try to look at how operating systems have written, using Windows and Linux on the last two classes. So how is the homework project 5 coming along? So people start to look at the code and stuff, right? Yeah, so the textbook is on the reserve. Inside the Linux book is on the engineering library reserve. So use that. That'll help you in terms of understanding what's going on, right? And the final exam happens to be on Monday. At official time is 8 to 10 in this classroom. Right. So I'm going to give you the take-home exam on the last day of class, and you can turn it in during that week. I'm not sure when I have to turn in the grades. I think the grades are probably the Monday after that week. So if you can turn it in by Friday, that'll be good. So I can give you the grades kind of thing, right? So if somebody really wants me to come in at 8 in the morning, I can. I would rather not. It's too early. But if you want it, then I would come, right? But you'll all have the cushion, so you can take it whichever time. Right. So are there any other issues? So one of the things that the colloquium speaker tomorrow is going to talk about, which may resonate. One of the projects that I've seen, he has way too many to mention, is. So there's a bunch of work which followed his work kind of stuff, right? So the essential idea is, in a file system, right? So what do you think a defragmenter would do? So I mean, if you use Windows, they have this defragmenter tool that you use to do something. It takes a while. You'll have some pretty pictures with like lots of bitmaps, and then at the end, everything will be on one side, and it says that's a good thing, right? What is it doing? What is it trying to achieve? Why is that all clumped up in one corner good? I actually don't know the answer, so yeah.
Well, isn't it anytime you request some memory, it has to find the amount of memory you request, and we talked about like looking for holes. You can either look for the first hole that it fits in, or you can look for the best fit hole somehow. But after you do this a lot, there might be a lot of spaces where you have a chunk of memory, and then a little tiny chunk of free memory, and then another file, and then another little tiny chunk of free memory. So it tries to put all the used memory together and leave your free memory in one big chunk. Yeah,
except all these are using blocks, right? I mean the storage system, you would assume is a block storage, so you don't have any external fragmentation, right? You only have fragmentation within your block. So any block is as good as anything, right? So yeah, if it is using variable size block, then hopefully this will do something, right? Yeah.
Is it moving around that program like the data on the actual hard disk? Is that what it's actually doing then?
Yeah.
So is it perhaps moving files to a way that makes it more optimal to read them based upon?
Exactly. So, yeah. Exactly. What, right?
To read the file faster, I guess.
Okay. So you had a
clipping on those lines.
Yeah. Yeah. Same idea. Get everything closer together, and the large free spaces. It's nice, but the real reason is so that your disk accesses are quicker.
So you would like them to be closer, right? So whatever meaning of closer, right? So you assume that the files are going to be used sequentially, right? Remember, that's why the closer works, right? If you're accessing all over the place, then closer really doesn't mean anything, right? But what you're really trying to optimize is when the requests are going to the disk system, those requests will be closer, not by any application, right? But it has to come. So if you have two applications which are doing stuff closer, and one happens to be on one end of the disk, one happens to be on the other end of the disk, then when it comes to the disk, it's all jumbled up and you're messed up, right? So if you were to do that, like assume that that's what you're trying to do, right? Where would you keep the blocks? So remember the disk, right? And let's say the track 0 starts here, and it keeps going out like that, right? So if you want to keep something sequential, would you keep it here, here, or here? There's no right answer. I'm just asking, right?
If you keep it on the outside, then there's more space because of the radius is larger.
Ignore those effects, right? Assume that that's not happening, right? I'm only talking about the seek and rotational seek issues, right?
But then if you keep it on the inside, the seek time, would the seek time be less? Or?
Would it be less or more, or what do you expect?
What are you saying?
The answer depends on the policy that you use, right? Depends on the scheduling policy that you use, right? So if you're using shorter seek first, then you tend to stay in the neighborhood. If you're doing a scan or something, you're trying to avoid those issues, right? Scanners, look, and all those things, you're trying to avoid those issues. So depending on what policy you use, depending on what the files actually use, it may or may not be good to have them in some location, right? And turns out it's not a trivial thing. You can't just look at it and say the file should be here, right? It depends on what else is happening in the system, right? So I actually don't believe that the defragmentation does anything you really want, right? Because yes, in some cases it does help. If you're the only process, nobody else is running, and the disk is free to just seek for you, then fragmentation might help. But otherwise, things are so jumbled up, it doesn't really matter, right? So one of the things that the visitor tomorrow was looking at was, so the observation is most disks are not full because you're buying big disks, right? So you could do this defragmentation on the fly. I think Macs do that on the fly, right? On the fly, they if they see that something is being accessed next to each other, they're moved to wherever they have to be, right? So technically, Macs should not need defragmentation because it can move stuff around. When the policies and when this happen and all those things, right? So their observation is, in a disk, let's assume that these are the segments which are actually used, right? The line ones, the rest are free, right? So if they are free, and if it turns out that under some circumstances, this particular stuff should be right here, under some other circumstances, this particular stuff should be right here, right? Because depending on what the file is, depending on what your working set is, maybe it should be here and it helps you. Maybe it should be here, it should help you, kind of thing, right? There are different reasons why, depending on scheduling algorithm, all those things, right? So their stuff is, if the stuff is free, just make a copy of this over here, right? And still leave it in the free block, right? Don't allocate it, but make a copy. Remember that you made a copy, right? And make another copy here. In the free block, it's still free, but it's actually copied. So if you were to do this disk reading, you can achieve good performance by reading this, but your disk will still appear like it's free, right? Your disk is fully used. So if you do this, your whole disk is copies of tracks, right? And those don't take up space because a free thing is not manipulated. You have to keep track of where those things are, and that way you get good performance and your disk works fine. And of course, the key is you have to make sure that you use this right, and of course you don't mess up your free block things. Of course, you don't want to. If you do it right, then you can benefit in all those things, right? I thought that's really cool. If you think about it, you have a large disk, it's not being used for anything, and it's internally replicating stuff when it thinks it needs it, but you don't lose anything. So if you need the space, it's still in the free block, so you can take it away. But as long as it's around, you get good performance, right? So that paper, I saw it in one of the top operating system conferences, stuff like that, right? So those are stuff that you look at and you go like, wow, that's a pretty nifty trick, right? The nice thing about operating system is you don't have to remember all the details about FIFO and all those things. You think of a problem, you think of what may be a solution, and you try to make them work, right? So hopefully you don't take away that it's a bunch of horrible algorithms that I don't understand. If you understand what's the problem, you ought to be able to come up with some solution and so on and so forth, right? So that's what I hope to talk about in the class today, right? So we have covered the four major modules of the operating system, in terms of the process, threads, scheduling, and memory management and file system, right? So when you think of what happens from operational state, right? You have a hardware, right? Some sort of a machine, and you want it to run your operating system so your applications can run, right? So you go through the startup or bootstrap process, and that's involved too, because that defines what your system can do. So it has to detect all the hardware, all the stuff in your machine, and it has to initialize all the state. It has to create all the data structures, and once it's booted up, it manages your resources. If you have a hard disk, it tries to manage disk, it tries to create something free, and it gives you the abstraction of processes and all those modules we looked at, right? From a functionality perspective, right, this is the most important stuff you want to remember is it's a glue between your hardware and the software, right? If the hardware does not give you something, then it's very hard for you to provide that in software. Your operating system cannot make this stuff up, right? So one of the things we saw was TLBs give you a faster way to access the your virtual memory translation, right? So the operating system can manipulate what goes into the TLB, move stuff around so you get a good TLB hit. But if you give me a machine with one TLB entry, right, there's not a whole lot the operating system can do, right? And so on and so forth. So if you don't give the right hardware, your operating system cannot work magic. Operating system cannot make some stuff up that you don't provide from the hardware, right? And that's one of the reasons I believe that Apples can get away with having the good name, right? Apple controls all the hardware to an extent that you don't randomly, they make some things obsolete right away, right? So for example, in Apples don't have serial port, right? If you have a PC, you probably have seen a serial port, right? Serial port, you probably have a parallel printer, you probably have a PS2 keyboard, you probably have a PS2 mouse, right? How many of you use PS2 mouse, right? So there's only one person, right? What do you use PS2 mouse?
Well, I don't have a USB mouse,
okay.
So I have a USB port on my computer and I have a USB to PS2 connector and
okay.
PS2 mouse.
So from OS perspective, it's still a USB key, right?
Yeah.
So the problem is, if I want to be able to access all these devices that you have, you may have floppy disk, you may have serial port, you may have parallel printer from some time, right? If you have to do all the stuff, the operating system has to be able to deal with those. It has to have drivers. It has to be able to talk to them. It has to have, so the code becomes larger and larger, right? And bugs creep in and bad things happen, right? So Apple's perspective is we control the hardware. We only give you the good hardware. So if the system is too constrained, we don't sell those machines, right? So all the machines that they sell right now is dual core, right? So that's that. I mean, so you don't run into a problem where you don't have too much hardware. So even though that's not under operating system control, that affects what the operating system can do. If you run your Windows on 166 megahertz Pentium with 30 megs of memory or something, it'll probably run, right? Eventually, right? You put the stuff, and eventually it slowly creeps along and stuff, but it can't do anything, right? And on the other hand, software is the one which, so if you don't have software to use what the operating system can provide, then it's no good either, right? So the software, I mean like POSIX, Win32, or what have you, right? And each of the operating system would define that as together, right? So if you look at Linux, you have a kernel, and you have all the other stuff on top of it, right? You have all the utilities and your GNOME window manager and GCC and all those things. Those are not operating systems, But if you don't go through them to use the stuff that it provides, it's of no use. So for example, if you don't use threads, if you have an application which does not use threads, right? So even though the fact that the hardware provides multiple processors, multiple cores, even though the OS provides the threads, if you don't know how to use it, if you don't use those stuff, operating system cannot make your application any faster too, right? So it has to depend on both of those stuff. So that's the important part. What does the hardware provide you? What can the application use? And if neither of them are broken, then you can't do much stuff. But if they both work, then operating system can actually give you a good benefits, right? So looking back at the bootstrap process, right? We never actually talked about what really happens, right? Bootstrap is a process where you power up the machine and eventually it comes to a point where it's usable, right? And so there's multiple different steps involved. So the problem is when the machine boots up, it knows nothing. It meaning like some entity knows nothing about what's in there, right? It does not know whether you connected a new CD driver, whether you connected a new mouse or what have you, right? So something has to understand, catalog all the hardware which is out there in the system, right? Create a list of all the hardware, what the capabilities are, and then progressively invoke applications which know a little bit more than the previous level, right? So you have a firmware which knows how to figure out what the hardware devices are. If it does not know how to deal with so you add a new hardware, it does not know what to do, then you can't use it in the system, right? So the firmware knows a little bit about keyboard, right? So it knows about keyboard, and it gives that to your master boot record program, which knows a little bit more about disks and stuff, because the firmware would have said there is a disk, and you happen to be on the disk, right? So, and the master boot record would say, okay, I know how to read my own disk, so let me read the next level, and so on and so forth, right? So you go through these different steps, and every previous step would tell the next step what is up there, right? So your boot program, your firmware would have to say what kinds of hardware you have, right? Operating systems can probe to see if the hardware is useful or what have you, but if the firmware itself does not detect them, then for the most part operating systems cannot do much, because it has to be done at the lower level, right? And it takes you a while, because it has to go through it. It figures out, it looks through all the system. The more hardware you have, the more it has to probe, right? And there's another reason why people don't like PS2s and stuff, because if there's a PS2 mouse, it has to say, okay, is there a PS2 mouse? Is there a PS2 keyboard? Is there a USB mouse? And so on and so forth. If you can cut down on those things, it's better, right? And this is a big problem. And a lot of people don't like to wait for machines to boot up, right? And especially this particular machine happens to be, I have no idea why, but it takes like 5 minutes to log me in, right? So how can you speed this up? I mean, this is a very important problem that Microsoft and all tries to address. I think Vista and all boots up faster, right? How would you solve this problem without telling how Vista does that? How would you solve the problem where if you attach a new hardware that I never seen before, I need to detect it. But on the other hand, if it's a device that I've seen before, there's no point in pretending like I've never seen something before, right? And reinitialize and make sure the device is still working, right? How would you solve this problem? How do you speed the login process, the boot up process? Your best case is as good as anything else. Yeah.
Could you boot essential hardware first, like boot just the keyboard and the mouse, and then maybe give the user some control, and then boot the rest of the things, like if there's a printer or something later?
Yeah, that's a good way to go about it, right? And that's what people are trying to figure out how to do that, right? Yeah, it'll be nice if you can boot up the barest minimum stuff. Basically do stuff in parallel, right? So I need let's say I need the disk, right? Because I need to know where the operating system is. But I don't have to know about all the hard disk. I only need to know where the master boot record is, know about it, give it control while I'm still probing other stuff, right? So that's one direction people are going. It's incredibly hard to do that because you're trying to figure out. So the best part is if things work out, you'll be fine, right? So if you get the stuff going, it is halfway booted up, it's fine, right? If things fail, like for example, you boot it up and you're going halfway through, and then you find that one of your hard disk is returning error, it can't boot up and stuff, right? So now you're in the state where half your system is kind of booted up and half the system is not booted up, right? Because there's error and you have to report it. So now you have to report this, right? Before, some of you may have seen, like if your machine does not have a keyboard, some of these machines will beep and say stop and say keyboard error, you have to press the keyboard, right? You can of course turn it off, but they will complain that you don't have a keyboard when they boot up, right? But in this system, you'd be halfway through Windows when it comes up error and will say no, there's no keyboard, I can't proceed, right? Because you went parallelly, so the firmware is still checking something else while your system is going, and how do you manage those is still a big problem, right? There is one device I know which actually does that, which is your Nikon digital camera. Many of you have seen the Nikon, the SLR cameras, right? Cameras have to go through the same issues of booting up and all those things. So when you power on your digital camera or your cell phone or whatever, you see for a while it's trying to do something. It doesn't come on instantaneously, right? So when it's doing those stuff, the camera has to see if the lens is there, if the lens is working fine, if the CCD is fine, and all those things, right? But I think those cameras boot up in like 0.7 seconds or something, right? Essentially, it assumes everything is working, it boots up, and for the most part, you're fine, right? You can start taking pictures. On the case where it has to fail, you'll fail in a bizarre way, because you'll look like you can take pictures, and then it may say there's no disk to store or something after the fact, right? But they figure it doesn't happen often, so people love the fact that it can boot up faster, right? Nobody likes to wait for the camera to speed up, right? So if you have a Nikon digital cameras and you start, and I think like Canon does that too. So if you look at the SLR cameras, they boot up really faster compared to the consumer version little cameras, which take like a couple of seconds to boot up, right? And they're booting up because using that same philosophy. Just assume everything works. If it doesn't work, then you can come back to it, right? And I think Vista and all caches all the drivers that it's seen, right? So that's one way to deal with that. So you keep a cache of all the drivers you've seen, assume that everything works, you load them up, right? And that works. So the future that everybody would like to go, I think Intel and all is working, is basically to leave a half-booted operating system in Flash or something, right? Rather than go through all this process, go through most of the process and store the image in the system. So when you power on, you essentially start already a half-started operating system and let it go, right? And that would be a good way to go. I mean, depending on if you add new hardware and stuff, then it'll slow down. But for the most part, the machine did not change. Like my laptop, I don't usually add too many hardware, so it can boot up basically a half-booted up operating system and go from there, right? So what would the problem be for that approach, where you have a half-booted up operating system and you just restart it from that every time? What would be the problem if you have a half-booted up operating system?
It might cause issues if you change the hardware on the computer.
Yeah.
If it's already programmed for that hardware.
Yeah, it'll cause problems if you have if you add new hardware, right? And more annoyingly, if a hardware that you already have failed, right, or partially failing, right? So since you don't do initialization and since you don't probe and make sure all the stuff, you assume it's working, and then you have to find that this particular hardware still exists but doesn't work, kind of thing, right? But these are important stuff. I mean, this may appear to be. We never talked about how do you speed up the booting process, but companies worry about that a lot, right? Because when people move towards laptops and stuff, you want your laptop to boot up right away, not wait for it to boot up after like maybe a minute, right? Minute doesn't sound that much bad, but if you're on the flight or something, you need to check your email real quick. You want the machine to be up real quick, right? So a lot of companies spend a lot of energy on those. So once you boot it up, right, once you boot it up, the issue is operating system is basically, in the best case, it's juggling these resources. It's making sure that it multiplexes the resources such that your application, your system would look like you have more resources than what there is, right? If there is plenty of resources, OS has no real job, right? If you have more CPU than you need, then it doesn't have to do the juggling. It can give the CPU to you and it's all done, right? If you have really fast memory, it doesn't have any job. So all it's trying to do is trying to make this juggling, right? And you have to remember that the one key thing to remember is whatever the operating system does to do any of this stuff is overhead, right? No one wants the operating system to spend thinking about what it has to do. So you want the operating system to manage the resources it has for your application, multiplex it such that it looks like you have more resources, and you want them with zero cost, right? Anything more is overhead, so nobody wants to pay for those, which means that typically you don't run very complex algorithms, right? So if you take an algorithms course, none of the first come, first serve and all those things would be considered to be a really great one, right? So you may talk about really complex mechanisms to schedule and stuff like that. We don't use any of those in operating system because we want them to practically take no time, right? Or if I do spend time, I need some guarantees that I will have some benefits, right? So we'll see what I mean when you think about servers. If I'm talking about a server, right, and I expect this application to run for a day, right? So if I'm Citibank, I bought this big machine to do my credit card processing, right? I know what this application is going to do, so I may run an algorithm which figures out precisely what's the optimal schedule for that particular application, right? Because it's very important, and I know the payoff for that stuff. But for the most part, most machines, if I know the future, then operating system can be trivial, right? So scheduling is trivial, and we don't know what the future is, so we're trying to predict based on what the past is. And since we don't precisely know what the future is, and since we're trying to predict anyway, right, why bother to make it hard, right? So that's the key that take from here. So all the algorithms we looked at, right, even if you forget all of them, even if you forget whether it was LRU and all those things, you have to remember that we were never trying to make it as complex as possible. We're trying to make it as simple as possible so it can be done really quickly, right? And if you don't understand that, then you're expecting the operating system to do stuff that it possibly can't do because you're not willing to give it the time to make the decision, so it has to do things really quickly, right? So the last question, right? So the future seems to be we are having more and more resources, right? I think if you buy a Mac, I think the default you get is like a dual core, 1 or 2 gigabytes of memory and so on and so forth on a laptop, right? So eventually we have lots of resources. What would happen to operating system, right? Assume that you have 32 core laptop processor, right? And assume that you're not running some application which require all the cores, right? So if you're doing this to run some, if you're giving this to Citibank processing something, let's assume that they will use the 32 core, they still want more, right? But assume that this is coming to your laptop, right? And most of us are not doing massive computations on your laptop. You're probably doing Solitaire on one window and if you're Windows, right? Solitaire is surprisingly a very powerful application on Windows, right? It's kind of funny because the National Science Foundation, it's set up where they have a bowl in the middle. The building is like a ring, right? And it's all glass up to 12th floor, right? So you can look inside and you see so it's like this. The building is like this, right? Offices all over here, and there's a skylight going down here. So from here you can see like all the 12 floors, including your floor, practically the whole building, right? So if you look from here, you see like, if you look for application, right? You can see the Solitaire because, I mean, you can tell the green screen with the little stuff, right? You can't really read it, but you can see the stuff, right? Surprisingly, it's like, and if you go this way, people are looking like very like they're working. But if you look from this side, you're like, oh, this is Solitaire, right? But anyway, so many of us don't really do massive computation on the laptops, right? So when you get to a point where you have let's say 32 core, right? What would process scheduling become? What would you do for process scheduling?
Wait for the next free processor.
I'm sorry?
Wait for the next free processor and ship it off there.
Yeah, if you have solitaire, I put it in one processor, and if the processor is not doing anything, I don't take it away from the processor, right? I mean, I just say, you have this processor, go have fun. I mean, you don't really need the resources, but I have so many resources that scheduling becomes practically trivial, right? I mean, as long as you don't ask for all 32. If you say, solitaire says, I want one processor, here, go ahead, right? And if you have like a calculator comes up and says, I want one processor, you give it, right? And since you don't have a need to take it away, this one application can have the processor all the time. There's no scheduling, there's no whatever. It's completely wasteful, right? From a typical OS perspective that we talked about, where you try to schedule different processors and stuff, but you don't need the stuff. So that may be a way things will evolve, right? Where your mouse may have its own processor, right? So your mouse will be pretty good, right? So actually, I mean, actually, you're laughing, but there's a company called Silicon Graphics. I think they're still limping around, right? So they used to be the graphics people, right? Silicon Graphics was the place. I think Cray bought them, and I don't know who owns them right now, right? So one of the things that they were, so I was visiting the lab, and one of the things that he was showing, one of the guy was showing was how smooth the mouse movement is, right? And if you notice your PC, look at your PC, right? Go to your PC and then move the mouse really fast, right? Even on the fastest processor that you do, you will never see your mouse. So if you move your mouse from here to here, right? It's likely that you'll see a mouse here, you'll see a mouse here, you'll see a couple of times here, like that, right? You'll never see the mouse smoothly go from here to here, where every little point you see it. If you move it really fast, right? Go check in your machine. I think you can try it on this machine too, right? Even though this machine may not be the fastest in the world, right? Right? So if I do like this, right? If you can see really fast, you may be able to see the mouse at some points, right? You see the mouse clearly at some points. The other points it's kind of going, right? It's kind of jerky movement, right? I don't know if you can notice it, right? The Silicon Graphics machine can actually show the mouse moving extremely smoothly across the whole thing, right? Because they have to have a mouse coprocessor kind of thing to do that, right? And it did matter because people are doing graphics art and stuff. Moving with this, where the thing is kind of jerky to exactly stay where you want to go was harder, right? But so you're showing up and saying, wow, this is really nice. And you're like, okay, who cares about the mouse, right? People do care, right? Especially when you're paying a lot of money to buy those machines, right? So on the other hand, if the resources are extremely scarce, what can the OS do, right? Some of you may read stuff like /dart where somebody would say, I'm running a Linux on iPod, right? People want to learn Linux on everything, right? So they want to learn Linux on this stuff, right? Like whatever this is. So they'll port Linux into this thing, and then there'll be a stuff with a screenshot of showing iPod running Linux, right? It's cool and all. It's sort of geeky and stuff. But what do you expect it to do? I mean, what can the operating system do in this device? What?
You can play Doom.
Yeah. I mean, no, but a lot of people would say oh, I run my Linux on the PC that my grandfather bought my father in 1980s. It's this 2 megahertz processor, and you should run Linux, right? I mean, I'm saying it will run. I mean, I don't doubt it will run, right? But I think it can run solitaire probably, right? Because I'm guessing solitaire is not too compute intensive. I've never played Doom, but can it play Doom?
Well, that's almost the only thing you can do on the iPod with Linux. There's not very much you can do.
Okay.
Preload it, just text editors and stuff.
Yeah, you're forgetting the fact that the input is.
You can use Morse code.
Okay, so yes, see that. Okay, that says it, right? Yes, you can use Morse code to enter in a PC, right? But realistically, right, many of us don't know Morse code, or I mean, when the hardware is cheap enough, right? So that goes in the philosophy of where the Mac goes and where the Windows goes. I mean, Windows does not go all the way to Morse code level, right? But at some point, you have to say, I know the machine still looks good, but it's just, it's time for you to upgrade and move on, right? Yeah, you can do Morse code to enter it on the keyboard, but, right? So making operating systems work on those. So when people complain that I have this old machine with like very little memory, and Vista does not work on those things, right? But what do you expect operating systems can do? I've never seen a Vista, right? But apparently Vista can have the nice GUI and the normal GUI, right? Depending on what graphics card you have, right? If you have two of those on the same operating system, you have to debug both the modules, and you have to make them both work. You have to keep these two stuff around, right? But at some point, you got to say, what machine you have is old, right? Just upgrade, right? And if you don't do that, then you end up with these cycles of having to maintain somebody's who has a serial port, who has a PS2, or who's typing in Morse code to enter text, right? Actually, is that true that you can enter in Morse code?
Yeah, there's two text entry methods. Like you can scroll through the alphabet on the bottom of the screen,
Okay.
or you can use Morse code.
Okay, I didn't know that, but that's too weird, right? So the module, the processes and threads we looked at, right? So the process notion was fairly straightforward because you have an application and we call it process within the operating system, right? And threads is a way for you to allocate more processes to a process, right? So threads, if you think about it, it's a fairly straightforward notion because that's the only way I can give you more CPU than one CPU. And then we looked at different ways of scheduling these things. And once you have many CPUs, you have the notion of synchronization. So it's all straightforward once you realize that all we're trying to do is you have a CPU and you're trying to give it to different applications. And if you want to give more CPU to application, then you're kind of forced into these notions, you're forced into the threads and all those things. The interesting part is how do you do scheduling? And I think in a couple of slides I have notion of how would you ideally schedule, right? Right now, if you know the future, it's good. If you don't know the future, you kind of use the past to predict what the future should be. And the thing to remember is if the hardware gives you support, you can do better. So the hardware gives you better support to context switch processors, then you perform better than the hardware does not provide, right? So for example, one of the things that SunSpark used to do, it may still do, is when you do context switch, they have a notion of register windows, right? So remember in the process control block, whenever you switch a process, you store all the contents into the process control block, and then you switch to the next application. So if you go from one process to another process, you store all the registers, all the state into the process control block, and let the other process run, right? So what they used to do was have a notion of register windows, where you have a large number of registers, right? Fast memory that you can use. You split them up into banks, let's say 4 banks, right? And you give them to process 0, process 1, process 2, let's say process 3. Each process only gets this much register, right? When you're doing a context switch, the hardware would switch the currently active register window from this to this, right? So none of these state is ever saved anywhere. It does a hard context switch essentially by switching from this register window to this register window. So your application has no way of accessing any of the other registers, right? But you pay no cost to save any state, or very little cost, right? The hardware itself in one operation can switch this. So when you do a context switch, all you do is you find the next process and you switch, right? All the registers are not saved anywhere. It's still there, right? Of course, if you want to bring in a process which is not here, then you have to do the stuff. But for the most part, you can do better. You can context switch much faster, right? Yeah.
What systems use this idea?
Spark. The SunSpark. And of course, it's incredibly wasteful, right? Because you have all these registers which you're not using. So that's the Wasteful means it becomes expensive. So Suns are not known for the cheaper Intel kind of stuff, right? But of course you get good performance. But from the OS perspective, if you have those, it's we can do stuff faster. If you have hardware support for synchronization, it's faster. If you don't have those support, they're not faster. So the question to ask is, how would you schedule for different kinds of applications like PDAs, laptops, servers, and desktops, and what have you, right? The problem is the same. I have a bunch of processes, applications I need to give the stuff. How do I give? When do I give? How long do I give? Depends on what I'm trying to optimize, right? If you're using a PDA or if you're using a Morse code machine, right? You have to give more privilege to the input. If you're a server, then you typically don't worry about input applications. You want applications to make progress and so on, right? And you're willing to pay for these kind of a costs. You're willing to have them go as fast as possible, right? And of course, the notion of memory management, right? Here the idea was, if all the memory was fast and cheap and you have plentiful, then OS has to do nothing, right? The memory management section would have gone away, right? But it turns out that's not the case. I mean, the fast memory is usually expensive, slow memory is usually inexpensive but plentiful, right? So you're trying to juggle these things. You're trying to make sure that the faster memory has the contents you want, and the slow memory has the contents that you don't want. And the best way you can do that gives you good performance, right? And of course, if your hardware does not support these levels, then the operating system cannot do anything. So if you buy a machine which has no TLB, then your performance will be slow, or very little TLB, you'll slow, right? So when you buy a laptop, technically you should be asking how much L1 cache do you have, how much L2 cache do you have, how much size you have, right? And the operating system can only give you whatever you get for that. And of course, those things are expensive. But given those things, it can move stuff around and make some process, right? And most of this stuff require a memory management unit. If it has to be done by in software, the performance will be so slow. So you need memory management unit, and depending on what it can give you, depending on what it can mark, depending on how it can let you know which process has to be swapped in, right? Virtual memory, when we looked at it, you can do different stuff. If the hardware can tell me how many times the page was accessed, I can do better stuff than if it only tells me it's been accessed or what have you, right? Again, it all depends on what the hardware can give you, right? And you have to have reasonable expectations on the hardware. The operating system cannot solve the problem if your hardware is so bad, right? And so I'm going through the notion of all these things faster because in the larger context, there's not a whole lot of brains in what we looked at, right? So in terms of the file system, you're trying to store objects in a persistent fashion, right? You want the stuff to be stored and be able to read it the next time you come up, which means that you need to have a way of naming stuff, which means that you need to have a way of organizing it using directories and all those things. But essentially the problem is, I want to store something and I want to come back and read it later, right? So how do I name the stuff so I can read it at some point, right? And again, so you have to optimize it for different kind of system. You have to optimize for small or large, sequential or random. And the answer to why you do defragmentation depends somewhere up there, right? In terms of if you're accessing sequentially, then you expect defrag to do something. If you're not accessing sequentially, then you don't expect defrag to do something, right? So think of Unix inode stuff, right? One of the things we asked in one of the homework projects or something is, the inode structure has this 3-level indirection stuff, right? So if you're accessing an object through those indirection mechanisms, even though it may be sequentially laid out somewhere, the way it's accessed is not what you intended. So this defrag won't really help you depending on how you go there, right? Think of linked list allocation, right? You're following these pointers, so you may not be able to read the next few blocks because you have to read the block to figure out. So if you do a linked list allocation, where you have the linked list pointing like this, right? Where the next block is where the pointer points to, it still may not help you because you have to read this block, and then find out the block that you wanted happens to be on the next block, right? So depending on how you set up, this may or may not help you. And one of the things to remember is when you're switching processes, when you're reading I/O, right? You have to pin down those memory, right? So for example, if you're writing something to disk, so you have a block that I want to write to the disk, so somebody else can use it, right? So I have a block which is dirty. It has to be returned to the disk. So I can give this block to some other process, right? So while this is being written, this block cannot be used by anybody else because it's still being written, right? So you have to mark this block as not usable, right? So even if I context switch and say this particular block, this new process can have, you can't have it immediately till the old I/O finishes, right? So you have some issues with those. So one of the questions I would like to ask is, what would happen when you have 32 core processor and you're doing disk I/O, right? So 32 core processor, let's assume you have 32 threads, right? And all of them are making requests for disk blocks. Some of them are making requests for disk blocks, right? Let's assume that only these are making requests to disk blocks. They all come down to the disk subsystem as, right? 5, 3, 1, some order, right? Some order of what you sent, right? So what would happen? What do you expect this to be? Slow or actually a lot, right? If you assume the rate that this one thread is asking is 1 per second, right? Here will be 5 per second, right? So this system will be pretty busy doing stuff. I mean, it's going to see lots of them, and it's going to see the whole bunch of jumbled up stuff, right? It may help it, it won't help it, depending on what the blocks are. So when you go to those processes, you may be forced to do RAID kind of stuff because otherwise your single disk arm cannot possibly support that much of I/O, right? So we may be forced to do something to speed up the stuff because instead of doing 1 per second, now I'm doing 5 requests per second, right? So the last one where I'll finish today was the notion of how should the I/O happen, right? So the I/O can be done either through some external controller or directly by the processor, which brings up the issue of one of the ways that modern operating systems deal with all this complexity is to outsource it to other processors, right? So you have the graphics controller, graphics coprocessor, network processor, disk controller, RAID controller, and so on, where the system itself does not do I/O, it gives it to DMA controller. It does not draw some lines, gives it to the graphic processor, and so on and so forth, right? So essentially your operating system is running a multi-threaded system, right? Where if it has to do some I/O, it gives it to the DMA controller, and when it's done, it gets the control back, right? And those are done by drivers, which you get from the vendor, right? So one of the key ways where these things begin to fall apart is if your graphics controller crashes, right? What can the operating system do, right? So right now it's no longer one operating system. It is running operating system. It calls the graphics controller using the driver that the vendor gave, and the graphics controller crashed, right? It had some bug, right? What can it do, right? There's not a whole lot it can do, but that's still a problem, right? Because now this reliability of the system is the sum total of all these components. And that's the important problem that all these companies would like to solve, where they can still fail something and be able to recover, right? Right now, if one of them crashes, the whole system will crash, right? We'll come back to this on Friday. But I want you to start thinking about these kind of stuff because that's the important stuff. And I think that's the reason why this course should be a core where you're trying to understand how do you build this stuff, right? And we'll continue on Friday.
Thank you.